The last concept we have to look at in this section is the idea of a residual. Residual is basically going to be the error between the actual value that is given to us from the original data set, and then also we're going to compare that to the predicted value. So if I was to plug the X value back into a model, it would give us a predicted value, and the actual data is what's given to us in the bivariate pair as the Y value. And so there's usually a distance between those, okay? We've already seen that before with our scatter plots and the points. And if we can plot those, we get a residual plot, those errors, all right? And residuals can be, or these errors can be used to identify anomalies or some sort of identify things that might not necessarily happen without some other influence outside. So for instance, maybe there's a recording error, or maybe it was a really hot day and it affected the pressure as opposed to other days, or maybe it was a very rainy day and it affected the flow of some sort of sewage plant or something like that. So what we're really looking for is we're looking for these sorts of data points that don't necessarily belong or seem like they don't belong in the original data. And then we can kind of look at the underlying concept as to why those occur. Residuals are easy to compute. You just take the actual value and subtract out the model from the data from the model value. And what we have down here is an example, all right? Notice that the further that a point is from this baseline of 0, and this basically says that there's no error between the model's value and the actual value. But that means that these are suspect points that kind of occur. So this is the original X values. These are the residuals, not the original Y values. And this just shows you how far that X value is, or that Y value is, given this X value. All right, so that's what a residual is. This is what a residual plot looks like, and these are essentially going to be our suspect points, the ones that seem to be further away. Knowing all of this, a lot of times that we know that data is stored in an Excel spreadsheet. Okay, it's probably one of the easiest ways to store data because then we could just access it really easily using Excel, and then we can go through and try to manipulate it, sort it, etc. But we know that Excel doesn't do everything that MATLAB does. And so that's our goal, is to have Excel talk to MATLAB and MATLAB talk to Excel, and they work together. So I have a scenario here where we're going to have some data, and which we have data recorded from an experiment that determines the percent of elongation in electrical conducting material. All right, and we know generally the hotter it gets, the more things expand as a function of temperature. All right, so the hotter the temperature is, the more that the percent of elongation should be. And just to show you what this data looks like, when the temperature is 200 degrees Celsius, we have a 7.5% degree of elongation in that circuitry. And then we just have this sort of relationship. All right, so now, since we're dealing with a section of linear data, we're hoping it's linear. Otherwise, we would have to hit it with one of those transforms and be able to make it linear. But in this case, I don't think it's going to be. So we're going to read the data from Excel, store it into 2 separate variables. We're going to compute the correlation coefficient. And then if it's nonlinear, then what we're going to do is we're just going to say it's nonlinear. We're going to do that check. And then we're going to find the equation of least squares line. We're going to print it. So this is all stuff we've done before. And then we're going to do a couple predictions. So this is all stuff that we've already done in the previous sections. Now this is the new stuff. Find the residuals and print them in a chart to the screen. Then we're going to print it into the Excel sheet. And then we're going to create a scatter plot with the original least squares line. And then we're going to construct a residual plot. The residual plot is going to help us to identify any suspect data. All right, so let's get to it. All right, first thing we need to do, if you probably remember, we need, when we're working with Excel, we need to get Excel into MATLAB. So what you're going to do is you're going to go into your file explorer. All right, now I already had mine pulled up. And I'm just going to take the spreadsheet and I'm just going to drag it over here. All right, so you probably remember doing that from one of the previous assignments. All right, so that's easy to do. We're going to read in the Excel data into MATLAB. All right, and you might remember that we have this command called XLS read. All right, so what I'm going to do is I'm going to say, I'm just going to call it A, because that's going to be the original data. We're going to say XLS read, and we're going to read the file elong. So elong.xls or elong, nlong, sorry, .xls. and we're just going to read it in to variable A. All right, now I'm going to open this up and then I'm going to close it when I'm done. But notice it does have these titles in here. All right, so now check this out. When I go through and I run this, and it might take a minute to actually run because I have to read it. And by the way, this is reading from a different place. Notice that A, remember that, and you might remember this from before, but A doesn't have that non-numerical heading in there, okay, which makes it really easy to work with, okay? Now, I'm going to store my two variables. So remember, this is the temperature. So the first column is our temperature. So I'm going to call this temp is going to be equal to, remember our command A colon, comma 1. All right. And I'm going to transpose that with that accent. All right. And I'm going to leave that off just to show you what happens. And then I'm going to say percent is going to be equal to A colon, comma 2, and then the transpose of that. Now let me run these just to show you what happens, just to remind you. And we're going to get our two variables, temp and percent, now as row vectors. If I was to get rid of these, they would be column vectors. All right, so we don't want that though. We want row vectors. So there we go. All right, so that's part A. We just read everything in, no headings, anything like that. All right, next thing we want to do is we want to, I believe, find the correlation coefficient and then print it to the screen. And then if for some reason it doesn't look like it's going to be linear, then we quit and we're done with this example. You could only be so lucky. So let's say R is going to be core coef of time or temp versus percent. And we are going to fprintf correlation coefficient is %f, and then go \n. And remember the trick, we're going to say, since R is equal to that, and then we want the first row, second column. All right. And then we do our if statement. So we're going to say if R 1, 2 is greater than or equal to -0.4 and R1, 2 is less than or equal to 0.4, then we're going to print an error message, and we're going to say data is not significantly linear. All right, which probably means that we probably need like some sort of other manner or other sort of model, if it is even indeed model, if it can be modeled. So let's just go ahead and run it. And notice I suppressed temp and percent. All right, correlation coefficient 0.989. So we're definitely good. And then the if statement did not print the error, so that works as well. All right, so looks like we've already done parts A, B, and C. Now we need the least squares line, and then we're going to do 2 extrapolations. All right, so we might just do those and end the video, and then we can start the residuals in the next video. All right, so least squares line. Remember, P equals polyfit of time or temp, comma percent, and we're going to do first degree. I'm going to do a sims variable up here. I have to do 2, so sims x, and also let's call it ls line just because we can. So we're going to say ls line is going to be equal to same command as before, p1 dot times x plus p2. And I believe it says that we need to print out the least squares line. So we're going to fprintf. We've done this several times. We're going to fprintf that the equation of the least squares line is %s. And remember, that's the string, and we're going to say ls line. All right, so that should take care of that. And we're running it, and we're waiting. All right, so here's our equation. Okay, that's good. Even though it doesn't necessarily mean much to us because, you know, it's got some weird numbers in there, or at least some numbers that we can't automatically, you know, just look at and digest. At least we have the least squares line. And that's the job of the computer, is to do those computations. Now we need to do a few extrapolation / interpolation types of things. So we're going to predict the percent elongation for a temperature of 400, and then we're going to predict the temperature when the percent elongation is 20%. So that means we might have to go backwards and do some solving. All right, so let's call it P400 for the 400 prediction. This one's easy. So P400 is going to be equal to P1 times 400 plus P2. That's easy, right? And we're going to say F print F. We're going to say when the temperature is 400 degrees Celsius, the percent elongation is percent F. And that's going to be P400. All right, now we need a prediction of 20. All right, and what we're going to do is we're actually going to solve for X. All right, so right here, we have our least squares line is equal to P1 times X plus P2. So since it's linear, it's really easy. So let's get another variable in here. Let's call it Y. And we're going to say, and we're going to call it, let's actually call it X1 and Y1. So X1, Y1, just so that way we're dealing with something different. And now Y1 is going to be equal to, let's just go ahead and solve it. So we're going to subtract P2. So we're going to say, actually it will be X1 is going to be equal to the quantity of Y sub 1 minus P sub, or P2. And then we're going to divide that by P1. All right, so all we're doing is we're just solving the least squares line. And then we could substitute directly in for X1. And we're going to subs, so we're going to say P20 is going to be equal to subs, and we're going to substitute back in for X1. We're going to substitute into Y1, and the new value is going to be 20. All right, so I mean, really what we could do is just put 20 right here, but just reminding you of that substitute sort of function. And then let's just copy this down here. And we're going to say when the percent elongation is 20, the temperature is, and we'll just do our percent F. And we're just going to change this to P20. All right, so let's run this and see what happens. I forgot the commas for both of these. So all of you are probably screaming at me like it's red underlined, why don't you fix it? Sometimes it's tougher to type, talk, and make sure it's the correct syntax. All right, so let's make sure these numbers make sense. When the temperature is 400 degrees Celsius, percent elongation is about 11%. And does that make sense? Let's look in the original data, and certainly should make sense because between 375 and 425 is 400. So between 10 and 11.3 is 11.07. So that one makes sense. And then percent elongation is 20, temperature is 864. So if we look at that, notice we don't have 800 on here, and we don't have 20 on here. So if we were to go down, percent elongation would be 20, like somewhere maybe like down here. And so if we kept going here, it might be like 800 something. So it looks like it makes sense to us. Okay, 864. Now, a little bit later, once we get the plots in here, we could certainly plot these points on the scatter plot and see if they make any sense whatsoever. But at least just from an initial inspection, it certainly looks like it makes sense. Okay, so that is, I believe, parts A through E, the stuff that we already know how to do. Now, in the next section, in the next video, what I'm going to do is I'm just going to focus on the newer stuff, the residuals, okay? And this one's a little bit new, but that wasn't too difficult to do. So we're going to go ahead, figure out what the residuals are, create a numerical chart, and then a graphical chart. We're going to print it back to Excel, and then we're going to get the graphical sort of representations for those. All right, so pretty cool stuff that we're going to be able to finish out with this.